We know that as we grow, the hurdles will be more. Each time we are washed away, we bounce back to the shore. We know we lead the way, keeping odds at bay. To see the sunrise tomorrow, inspire the world to follow.
So, in the course curriculum of Electrical Machine 1, in module number 2, today on the topic of DC machine, we are going to discuss voltage buildup in DC generator. Okay, and the objective and outcomes of today's lecture is to become familiar with the voltage buildup process of DC machine. So let's start lecture number 7 on voltage buildup. So when the shunt field winding of a DC generator is connected across its own armature terminal, the way shown in this figure, a small voltage due to residual magnetism is impressed across its field, is impressed across its field. So if we connect the shunt field winding across its own armature in this fashion, which is shown in this figure, a residual magnetism will be impressed in the field, and it is assumed that the left pole is north pole and the right one is the south pole due to residual magnetism, and it also assumes that the armature rotating in clockwise direction. So if the polarity and clockwise rotation of armature we assume, then the polarity of the brush will be top one plus and this one minus. Okay, so the top brush to be of positive polarity. The small voltage produced by this residual magnetism, because if there presents a residual magnetism, there will be a flux cutting and there will be a small voltage produced due to this residual magnetism. Now when, so due to residual magnetism, there is a production of induced voltage, and which in turns result in a flow of small current through the field turns, which results in an MMF, which results in an MMF that acts upon the residual magnetism. If the resistance of field winding is sufficiently low, that means if RF, that is field winding resistance, is sufficiently low for the speed at which this dynamo is running or generator is running, the field flux will be increased. Means it is additive in nature for this particular connection. And this increase of flux again causes increase in generated EMF, which again increase the current, which again increase in the MMF, and which cumulatively increase this induced voltage or generated voltage. And this cumulative process of generation of voltage in DC generator is called voltage buildup or buildup of a generator. Now the next question that arise into our mind, that how long this cumulative process goes on continue. The answer is that it will continue up to the point of equilibrium. It will continue up to the point of equilibrium. So that means we have to now decide the point of equilibrium. Now so this is the point of equilibrium. Okay, and this is the OCC, open circuit characteristics curve of DC generator, and this is my excitation line. Okay, it is a straight line, follow y equals to mx equation passing through the origin, because V equals to I into R. RF is the resistance of the field circuit, IF is the field current, and suppose EF is the generated voltage. So the resistance line, so this is basically y equals to mx. So this is my excitation line. Now equilibrium will be reached when generated voltage, that means this is the generated voltage in this point of where this field resistance line, where this field resistance line and OCC curve intersect with each other. So in this point, this is the generated EMF, and for generation of this amount of voltage, what is my current? This is my current. Now if this amount of current is flow through the field winding, in turn it will produce only this amount of voltage. So you should be very clear, for generation of this amount of voltage I require this amount of current. The vice versa is also true. If this amount of field current is flow through the shunt field winding, the voltage generated is this much. So this point is the equilibrium equilibrium point. So equilibrium will be reached when generated voltage causes a current, when generated voltage causes a current in the field that is, suppose I have taken this amount as IF1. Suppose I have taken this as IF1 in the field when the generated voltage causes a current in the field which corresponds to the exact excitation required for the generation of this EMF. So this is decide the equilibrium point. So that means if I taken this value as EF1, suppose, so when the generated voltage, that is EF1, so for the generation of this amount voltage EF1 in the armature, the current which is flow through the armature is IF1, and this IF1 is required for generation of this much EF1 amount of voltage in the armature. So this is the point of equilibrium. Now since the building up process start with residual magnetism and proceed in the direction of increasing potential across the field, the ascending branch of magnetizing curve will be used in all discussion relating to the building up of the generator. So this is my area of discussion, ascending branch, up to the ascending branch. Now the excitation line is plotted as I have mentioned from EF equals to IF RF. So RF equals to IF equals to EF by RF, where IF RF is the total field resistance including the rheostat, and I have mentioned this is a straight line passing through the origin. Now this residual magnetism causes the generation of voltage ER. Now due to the residual magnetism, you see there is a small voltage impressed in the DC generator which is ER, which sets up a current in the field as I have mentioned. Now this field current produces a flux which is added to this residual magnetism and thus generated a voltage greater than ER of any instantaneous voltage. Suppose I have taken at this point, at any instantaneous value I have taken EX, I have taken EX, impressed on the field. So EX now impressed in the field. Now EF is sufficient. EF is this amount voltage. At this particular point, the impulse voltage in the field is Ex. But this voltage, that is my EF, this EF is sufficient to overcome the field resistance drop due to Ix. So for this amount of current, this EF is enough to overcome this field resistance drop. But now the voltage is Ex. So what is the extra amount of voltage is Ex minus EF. So this is my extra, because EF is enough to overcome the field resistance drop. So this difference Ex minus EF is available for this acceleration or cumulative process of voltage build up, and this difference in voltage will increase the current. Now as long as this difference is exist, now suppose I have taken in this point, suppose here it is Ey, okay. So and this is my EF2. So this EF2 is sufficient to overcome the field resistance drop, but this extra amount will increase the current, which increase the induced EMF, which increase the induced voltage, and this process is go on as long as this difference is exist. Now if you look in this equilibrium point, the difference is vanished. Okay. So this is, that's why this point we call the equilibrium point. Now the accelerating voltage, that is Ex, this is known as accelerating voltage. Accelerating voltage. So this accelerating voltage is opposed by an EMF of self induction induced by the field, by the change of field flux, because whenever there is magnetic circuit, there is induced EMF due to change in the flux. So the Lenz's law always comes into the picture. So this is opposed. So that means Ex minus EF equals to NF d phi f by dt. d phi f by dt. Okay. Since now what is my EF? EF is my RF, IF, RF. So what is my Ex? My Ex is Ex minus EF plus EF. That means NF d phi f by dt plus IF RF. So this equation is the equation which is governing any change of voltage and current in an inductive circuit. So this is the equation which is responsible for any change in voltage current in inductive circuit. Now as the generated voltage rises along the magnetizing curve, the point En is finally reached. This point I have reached. Till before this point, this accelerating voltage is exist. At this point, the voltage generated is just equal to that required to produce an excitation which will cause it. Okay, the stability of this point can be shown by considering what would happen if the voltage should overrun to some point Em. Okay, so I am analyzing the stability of this point. So suppose somewhere it overturned to up to this point Em. Now point Em on the magnetizing curve corresponds to a field excitation which require a field voltage Ef. So in this point, this is the field current, this is my field resistance line, it is intersecting at that point. So Ef dash is the required field voltage. Now obviously this field voltage is not available because the available voltage is this, but my requirement is this amount. So this extra amount Ef dash minus Em is not available for self excitation, and the generated voltage of Em cannot be maintained. So we cannot maintain this voltage M. Therefore the intersection of this field excitation line and the magnetizing curve represent the voltage to which a self excited generator will build a voltage at no load. Okay, so this is the concept of voltage generation of DC generator. So we will end our lecture, today's lecture, here. In next class we will discuss the critical resistance and the critical speed related to this voltage build-up process. So these are the books you can refer for your study. Thank you very much. So this is the end of today's class. Thank you very much.